Anomalies in ionization energies. Let's look at this figure. On the y-axis, we have ionization energy. So here, as we're going up, the ionization energy, what does that mean physically? As it's going up, it's getting harder to remove an electron. Okay, and then the lower the ionization energy it is, the easier it is to remove an electron. Okay, so let's now look at this, the atoms. Looking at hydrogen and helium, why is hydrogen lower and helium higher? Well, helium is a noble gas. And so it's already happy. It does not want to lose an electron. Okay, now let's say I'm going to look at neon. Neon is also really high. Why is that very high? Really, it's the same reason, because it's a noble gas. It already has a full shell, so it does not want to lose an electron. Same thing with argon. Okay, now there are a couple of anomalies that happen. One is this beryllium. If I look at lithium, lithium is fairly low. Why would lithium be low? The last subshell that lithium is in is the 2s1. If lithium removes one electron, it becomes the same as a noble gas, which would be helium. So if it has the same electron configuration as a noble gas, it's really happy. So lithium will want to remove an electron. Okay, now beryllium is kind of higher, but then after that, boron, the next one, boron, it goes down. Shouldn't it just keep going straight up? So we're going to look at beryllium and magnesium, and we want to know, why does this occur? Here I gave the electron configurations for 4 different elements: beryllium, boron, magnesium, and aluminum. Let's look at beryllium first. Okay, let's say I am going to look at the first ionization energy. First ionization energy, if you remember, you're removing one electron. So beryllium, because you're removing one electron, turns into a cation. The electron configuration would therefore be 1s2, 2s1, because you're removing one electron. Now, if I looked at boron, I remove one electron, so it turns into B positive. We get 1s2, 2s2, and that's it, because we remove that one electron in the p orbital. Okay, well, which one does not want to lose an electron? Beryllium, because this has a full subshell. If I look at boron, however, it can more easily remove an electron, because then it turns into a full subshell. So it can more easily remove one electron. And we have this new vocabulary word, so it becomes isoelectronic with isoelectronic means it has the same electron configuration as beryllium. Now beryllium has a full subshell already, so it's happy, 1s2, 2s2. If we look on the figure before this slide, we said that beryllium has a higher ionization energy. And the reason why, because it does not want to lose an electron. Boron, however, is going to have a lower ionization energy. The reason why is it can more easily remove one electron. Okay, so we kind of compare beryllium and boron. Now let's look at magnesium and aluminum. Again, I'm going to look at the first ionization energy. So I'm going to be removing an electron. Removing one electron turns it into a charge, a positive 1 charge. So let's remove an electron. So instead of 3s2, we remove 1, so we get 3s1. Same thing with aluminum. And because we remove one electron, we have no electrons in the p orbital. Okay, now which one does not want to lose an electron? Magnesium. So it does not want to lose an electron. Because, why? Because it has a full subshell. If I now look at aluminum, if it loses one electron, it turns into a full subshell. So it actually does want to remove one electron. So aluminum, it can more easily remove one electron, so it can have a full subshell. If I look on the figure on the previous slide, we saw that magnesium has a higher ionization energy. The reason why it has a higher ionization energy is because it does not want to lose an electron. Aluminum, on the other hand, will have a lower ionization energy, and the reason why is because it can more easily remove an electron.